Let's talk about using physics to numerically simulate a system. My name is Jorge, I'm a physicist, and we're going to do the 3D n-body gravitational problem with inelastic collisions, and we'll talk about what all that means. First, the n-body. Each body contains a set of attributes. They are the position, velocity, mass, and radius. Our task is to determine how these attributes evolve in time. The mass and radius don't change. The velocity evolves according to Newton's second law, which says that mass times acceleration, which is the rate of change of velocity, is equal to the sum of the forces. And then once we have a velocity, the rate of change of position is the velocity. So we can solve that differential equation. We have n of these. Let's calculate the forces. Acceleration due to gravity is equal to the force of gravity divided by the mass for that ith particle. And it is the sum of the gravitational forces from all of the other particles interacting in the sim. The only augmentation of the typical gravity that we have is this epsilon term. It's called the Plummer softening, and it basically keeps the gravitational acceleration from getting too large. So if the particles get closer to a certain amount, then it just becomes a constant. And this is for numerical stability. Let's talk about our contact forces. These are inelastic collisions. An inelastic collision is one where kinetic energy is not conserved and momentum is conserved. Think of two putty balls thrown at each other sticking together. These collisions only happen when the particles are a certain distance apart. There are two terms associated with these collisions. There's the regular spring term right here that depends on how far these things are. And then there is the dashpot term, which depends on their velocity. And this is the one that causes dissipation of kinetic energy. You have your spring constant, and then you have your dashpot term. And it is this energy dissipation which causes the flattening of the system into a disk. Now that we have these two accelerations, we can put those together in this expression above. Here's your gravitational piece. This is your collision piece. With the theta right there, that's a step function. It just says that the collisional terms only turn on when the objects are closer than the sum of their radii. Now we need to integrate this system. By integrate, I mean given an initial position velocity shown above, how does this evolve in time? What's my next position and next velocity, the delta t away, where delta t is a small increment in time? Well, we use kick drift leapfrog integrator. It takes your current velocity and the delta t and splits that delta t in half. We calculate an acceleration given our position and velocity. We take our current velocity and we add to it the acceleration times delta t over 2. That propagates our velocity to a half step of delta t. And now we take that velocity to propagate the position, a full step of delta t. We take our current position and add to it that velocity we just calculated times delta t. We go back and take this position, calculate a new acceleration from which we propagate our velocity the other half delta t. This is a fairly stable numerical integration method, and it conserves energy up to delta t squared. We have positions, velocities, we calculate forces, divide those by mass to get accelerations. Once we have all of the accelerations, we can take those accelerations to propagate our velocities forward, and we can use those velocities to propagate our positions forward. And this is how we numerically simulate a system with large numbers of particles. There's about 35,000 in the simulations you've been watching above. Physics is basically predictive data compression.